In this lecture, we're going to provide an overview of correlational and regression analysis. So some of the key points when we talk about a correlational study, the first step is to identify what's called the criterion variable. Previously, we referred to the variable on the y-axis as the dependent variable, but when we conduct a correlational or regression type of study, the y-axis is typically referred to as the criterion variable. The variable listed along the x-axis, typically referred to as the independent variable, is now referred to as the predictor variable. So once these two axes have been identified, the very first step before we get to any computations is to make a scatter plot of the data, and then we perform what's sometimes referred to as the intraocular test. And this is basically the researcher looking at the graph and gaining a subjective estimate of the pattern that emerges from the scatter plot. So it's very important that the researcher generates a subjective impression before carrying out the statistical calculations. So some of the questions include, does it make sense? Do these data look like the pattern or demonstrating the pattern that we might expect? And then can it be explained in terms of the original field and the original discipline, so from a sociological, anthropological, or political sense. And so we start with this example examining hours per week spent on housework, number of children, and a number of families that were sampled. So this is an example out of the textbook where we see two different displays of the data. The first display on the left-hand side is the data in tabular form, and on the right-hand side is the scatter plot. So here we see the number of children per family listed on the x-axis. So this is our predictor variable, and along the y-axis is the housework in hours per week, and that is what we now refer to as the criterion variable. What we see here is depicted on this graph is something called the line of best fit. So we have all the data from the table, and those data from the table are plotted, and the line of best fit is just as the term suggests. It is a line that is drawn through all of the data that best describes and approximates the location of all the points with respect to the line. If we take a look at the first family, family A has one child, and 1 hour is spent on housework, we see that data point is plotted accordingly. But now if we focus on another data point, in this case we have a family with 2 children where the number of hours spent on housework is also 1 hour. This actual blue symbol is the actual value that was put on the plot from the actual table. And so this data point would correspond to family F, where there are 2 children and 1 hour spent. The corresponding point on the line that matches up with this with the number of children on the x-axis is what we call the predicted value. So we have 2 sets of data on the scatter plot. We have the actual data, which were transcribed and transferred from the tabular form, and we have the line of best fit that attempts to predict the number of hours based on the number of children. So a second example here is examining body mass, how much a person weighs, and this is the predictor variable. And so in this study, the question here asks if body mass is a good predictor of muscular strength. And that is our criterion variable. Sometimes referred to as the dependent variable, but when we examine a prediction, when we take a predictive kind of approach, then we just refer to it as the criterion variable. Here we see the real data, the actual data plotted from a number of research participants. And we have the line of best fit that attempts to predict what body mass, what muscular strength will be based upon body mass, but we also see the scatter around the line of best fit. So when we move on to correlational analysis, we're examining two things. We're examining both the direction and how strong the relationship is between two variables. And this provides a degree of, or provides us with a measure of consistency between the two variables. So the variability in y-scores is going to be paired, or at least our examination will examine that variability as it's paired up with x-scores. In the latter part of this unit, we'll focus on something called regression analysis. And in regression analysis, we examine how close the scatter plot fits that regression line, or the line of best fit. So the two different terms are used interchangeably. And in doing so, we can then test the relative accuracy of a prediction. So when we take a look at some positive relationships, in these two examples, we're going to predict muscular force, how strong a person is given the size of their muscle, muscular girth. So is muscular girth a good predictor of how much force a person will generate? And so with the idea that people with large muscle girths are likely to produce more force. The key concept to remember when we talk about correlational or regression analyses is that we are not establishing cause and effect. Different research designs are necessary to do that. Now, if we move to the hypothetical figures on the bottom part of the slide, here we see a measurement of muscular force with the relative units and muscular girth with the relative units. And so this aligns with our original question where muscular girth is the predictor for how much force that muscle can generate. And so when we take a look at the scatter plot on the left, here we see every single measurement from all the research participants line up perfectly on the line of best fit with no difference between the data, any of the data points, and the actual line. And in this case, the statistic that is generated from a correlational analysis is something called the R statistic. And the R statistic is a measure of how strong that relationship is. If we see that the line cuts through every single data point, then it has a perfect correlation of 1.0. Now, most research studies, the vast majority of research studies, do not have this type of, or rarely have this type of finding. And so what we actually see is the scatter of the data, but the data are scattered in a fairly tight distribution, and the results from this study yielded an R value of 0.94. So a little bit less than 1.0, but still a very strong correlational value that relates muscular girth and force production. And both of these relationships, because as the x-axis increases on both, the y-value axis increases as well, that's a positive relationship. The opposite of that is a negative relationship. And so in these graphs, we're going to examine people who spend more time going to the gym. Are they likely to have less body mass? Are they likely going to weigh less? And so the key here, once again, is that this type of approach does not establish cause and effect. So it does not necessarily mean that by spending more time in the gym, it will decrease a person's body mass. A different research design would have to be incorporated to establish that cause and effect relationship. But in this approach here, we're getting one snapshot in time from a number of research participants. So along the y-axis, we have a measurement of what's called lean body mass in kilograms, and the amount of time people spend in the gym per week. And so on the left-hand side, here we see information that was obtained from a number of different research participants, and this R value indicates a strong relationship. 0.85 is a rather high number. The maximum number that can be obtained is 1.0. But what we see is as the number of hours spent in the gym per week is greater, the people are likely to have less body mass. And that is a one snapshot in time investigation as the individuals were sampled for that information but were not followed over time. So once again, with the reminder that this is not cause and effect. We see on the right hand side, once again, an example of a perfect correlation. So we have the values, the negative values indicate that as the magnitude of the x variable increases, the magnitude of the y variable decreases. So the first thing that we've established here is that the next thing we've established here is that the correlational statistic of the R value can range from a negative 1.0 to a maximum of positive 1.0. Additional approaches, additional studies are more likely going to reveal these possibilities as well. So with the graph on the left-hand side, here we see a study with a scatter plot that generated a correlational statistic of 0.44. So what do we take from this type of analysis? The key points is that, first of all, it's a positive relationship. That's the first thing we need to investigate, we need to establish. So as the value along the x-axis increases, so does the value along the y-axis, but we see so many data points that are further away from the line of best fit. And so this would be considered a weak correlation or a weak relationship because of that greater distance of so many of the data points from the line of best fit, but we can still observe this upward trend from these data. So on the right hand side, we see a research study that yielded a correlational statistic of 0.00. And the key point here is that we would not describe this as positive or negative. We would just simply describe it as no relationship. And we just even with a visual observation, we see that there is no pattern that emerges from this scatter plot. So just to touch on some of the key points to the correlational analysis, it's also referred to as the Pearson product moment correlation. And whenever when we start talking about and calculating the R value, it is the PPMC. It is actually the Pearson R value. So there are multiple ways to make reference to this symbol. So the Pearson product moment correlation does determine the strength of a linear relationship between two variables as we step through the computations. The greater the R, the more predictive the relationship, understanding that the maximum range is negative 1.0 to positive 1.0. The value indicates both the direction and the strength of the relationship. So when we have the value, if we don't have a negative sign in front of it, then the value indicates it's a positive relationship. When we have a negative value, it indicates it's a negative relationship. Once again here, a high correlation, so a very strong correlation value that's close to 1.0, even though it's very high, it does not prove causation. Nor does a low correlation eliminate causation. So to establish causation, cause and effect, additional studies would have to be conducted with very different types of experimental designs. And the PPMC relies on the concept of covariance. And so the scores along X will have a certain variability, the scores along Y will have a certain variability, and the question here is, how do those two variabilities relate to each other? In this illustration on the right-hand side, here we see a negative, or also referred to as an inverse relationship. And in this case, this is a perfect relationship because all the data points line up on the line of best fit. And so we would conclude that this particular graph would have an R value of negative 1.0. So this ends the first part of our correlational unit.